Hi everyone, my name is Rutuja and welcome back to DataToCrunch. So right now we are at the initial stage of learning Spark and Databricks where we are trying to cover some important theoretical points. So now let's dive in and start crunching some concepts together. So today we will try to look into the points which are getting displayed on the screen. We will try to see how this Apache Spark has evolved significantly since its inception, starting with the RDDs as its foundational abstraction, and over the time how this Spark introduced data frames for more user-friendly and SQL-like interface, and afterwards how datasets came into scenario to combine the benefits of both RDDs and data frames all together. And afterwards, we will try to look into Spark ecosystem, and lastly, we will see how these RDD operations function. So as I told you in the last lecture, I have divided the coming up next points into two parts because of the time constraint. So in this lecture and in the next lecture, we will try to cover all those points. So now let's move ahead and see Spark API history. So Apache Spark APIs has evolved over the time to make big data processing more efficient and user friendly. So the first evaluation is RDDs, which is nothing but resilient distributed datasets. So these were the first APIs introduced in the Spark. So they provided a low level fault tolerance and distributed way to process the data. However, these RDDs require developers to write some complex and verbose code, which makes it harder to optimize the performance. So to address these challenges, data frames were introduced. So these data frames simplify big data processing with high level abstraction, which is inspired by the SQL tables. So DataFrames offers these optimizations through the Catalyst Optimizer and Tungsten execution engine by improving the performance significantly. However, we can say that they lacked a type safety which could lead some runtime errors. So to combine these benefits of both RDDs and data frames, Spark introduced the next type, which is datasets. So datasets provide the type safety of RDDs along with the optimization capabilities of data frames by giving the developers both control and the efficiency. So this, in short, we can say that this evaluation reflects the Spark's commitment to make the data processing more declarative, optimized, and easier to manage. Now let's see all these three concepts in depth. So the first one is resilient distributed datasets. So RDDs are the foundational API of Spark, and those were introduced when Spark was first created. They also provide a low-level abstraction for distributed data processing, and along with that, they are immutable by design. So what is meant by immutable? So that means that RDDs cannot be modified once created, which makes sure that dataset state is consistent across the cluster, even in the event of failures. So this immutability is what makes the RDDs fault tolerant, as each of these RDD contains a lineage graph. So lineage graph is nothing but a record of all transformations which are applied to the data. So if a partition of an RDD is suppose lost, Spark can recompute it using that lineage information from the original RDD, which makes sure that there doesn't have any manual intervention into it. So the next one is transformations such as map, filter, flat map. Those are lazy operations, means that they don't trigger the execution, but instead they just define a series of computation steps. And after the transformation, actions like count, collect, reduce, save, those trigger the execution by submitting the jobs to the cluster. So we can say that while RDDs provide a control over the data, they also come up with high complexity and verbose in the code. So developers needs to write the explicit code for the operation like caching, partitioning, and optimization, which can be difficult for large scale operations. So additionally, RDDs also lack internal optimizations, which leads to the inefficiencies in the execution, especially in the complex queries. So if we talk about RDDs versus data frames and data sets, we can say that while RDDs are most flexible APIs, they require most efforts for the optimization. So when dealing with the large data sets or complex operations, the absence of these automatic optimizations makes the RDDs less efficient as compared to the high level abstractions like data frames and the data sets. Now let's see about the data frames. So data frames were introduced in Spark 1.3 to provide high-level abstraction that simplifies the working with structured data. A data frame is essentially a distributed collection of data organized into named columns, which makes it analogous to tables in the relational database or maybe a data frame into R or pandas. So this tabular structure makes the data frame more easier to work with as compared to RDDs, especially for the developers who are familiar with SQL or data science workflows. So if we talk about the characteristics of data frame, one of them could be optimized execution. So data frames automatically leverage this Spark's Catalyst optimizer for query optimization. The Catalyst optimizer performs these logical optimizations such as maybe constant folding or predicate pushdown or projection pruning to reduce the computational complexity of the queries. So this leads to a significant performance improvements without requiring the developer to manually optimize the code. In addition to Catalyst, Tungsten execution engine is also employed by the data frames for the physical optimization. So Tungsten improves the execution by focusing on low-level optimizations, maybe such as in-memory processing or cache optimization or columnar storage and memory management, which significantly boosts the performance by minimizing this disk I/O, and it also speeds up the CPU processing. We can say that data frames also has SQL compatibility. So data frames can be queried using SQL expressions, which makes them highly compatible with the SQL users. So you can perform transformations using DataFrame API or register them as temporary views and execute the SQL queries on them by providing a most familiar interface for the SQL developers. So if we talk about data frames versus RDDs, so data frames are generally more efficient than RDDs because they allow Spark to apply optimization through a Catalyst and Tungsten engines. However, they offer less flexibility compared to RDDs because they impose a schema on the data which can be restrictive when working with highly unstructured or heterogeneous datasets. Additionally, data frame like type safety also, which refers to ensure that the data types are checked at the compile time. So that means that this type safety is error related to the data types, and that can be only caught during the runtime and not at the compile time. So now let's see about the data sets. So datasets were introduced in Spark 1.6 as high-level API that combines the benefits of both RDDs and data frames. Along with that, datasets bring type safety to the table, which allows the users to work with strongly typed objects. It also allows compile time type checking by reducing the error related to data mismatches that would otherwise occur at the runtime. So type safety means that system enforces the correct usage of data types at the compile time by making sure that operations maybe such as mathematical calculations or the transformation or comparison, those are performed only on the compatible data types. So for instance, let's say suppose you are working with a data set in Spark, and if you try to apply string function to an integer column, Spark will raise an error during the compile time only rather than making or raising this error at the runtime. So this is what type safety means. Apart from that, datasets retain all the optimizations that DataFrame provide, which mainly includes Catalyst and Tungsten. And along with that, it also adds type safety to that. So this makes the datasets especially appealing to the users or the developers who want the performance benefits of data frames while still maintaining the benefits of strong typing from the RDDs. So if we talk about the API interface, datasets allow for the mix of both functional programming operations and SQL-like operations. So this duality provides the developers with the flexibility to choose the programming style with which they are most comfortable with. Dataset also supports both typed and untyped transformations, which makes them versatile for both structured and semi-structured data processing. And about the performance, since datasets are backed by the same execution engine of Catalyst and Tungsten as data frames, they benefit from the same performance optimizations, we can say. This also these optimizations also involve the use of Tungsten for memory management and code generation, which compiles the query plan into bytecode for the better performance. So this gives the datasets a best of both world advantage. That means that they can combine the ease of use and the optimization of data frames with the type safety of RDDs. So if we talk about the data sets versus data frames, the key difference between data sets and the data frames is type safety only. So data sets are type safe that and can be statically typed to avoid runtime errors, while data frames are not type safe and we can work with generic objects into the data frame. So data sets are ideal when you need to compile time safety, while data frames are better when you are working with untyped data or when the performance is a primary concern and time safety is not critical at that time. So in conclusion, we can say that each of these APIs serves different purpose depending on the need of application. RDDs are the most flexible and provide the low level control, but it also requires more efforts for the optimization and code complexity. Then the data frames offer high level abstraction with the automatic optimizations through Catalyst and Tungsten, which makes them ideal for the developers who are seeking for the simplicity and the performance. And finally, we can say that data set combine both RDDs and data frames along with offering this type safety with the optimizations of the data frames. And it makes them suitable for the applications where data integrity and performances are critical. Now let's see about the Apache Spark ecosystem. So this ecosystem is a comprehensive collection of the components and the libraries that come together to deliver fast and scalable data processing solutions. So whether it's handling maybe data processing or batch processing, real-time streaming or machine learning or graph analytics, this Spark ecosystem, it offers a range of tools to manage this big data task very efficiently. So the first core component is API. At the heart of Apache Spark ecosystem, this Spark Core API lies. So it is a foundation that powers the distributed data processing. And Spark Core manages essential tasks such as task scheduling, memory management, and fault recovery by ensuring a smooth and efficient execution across the cluster. So one of the key innovation introduced by Spark Core is RDDs. So these are immutable and distributed collection of the objects that allow parallel computation on these large data sets. So with RDDs, you can perform transformations and actions while maintaining the fault tolerance and the scalability. So the next component is Spark SQL. So Spark SQL is a module designed for working with structured and semi-structured data through SQL-like queries. Spark SQL introduces DataFrame API, which organizes the data into rows and columns, much like a relational database table. So this makes it easier to work with structured data, and it supports various file formats such as JSON, Parquet, ORC, and even Hive tables. So the power of Spark SQL lies in its ability to run the SQL queries on data stored in these different formats by offering the users unified approach to query the data. It also integrates seamlessly with the BI tools, making it ideal for data warehousing or ad hoc analysis by simplifying the workflow for the structured data processing. The next one we can talk about is Spark Streaming. So for real-time data processing, this Spark streaming is an essential component. So this module enables the ingestion of real-time data from sources such as Kafka, Flume, or TCP sockets, and it processes it into micro batches. So it provides fault-tolerant stream processing, ensuring data integrity and the consistency. Additionally, Spark Streaming supports advanced operations like windowed transformations, which allow analysis over the intervals. So it integrates seamlessly with the other Spark components, maybe like MLlib or the GraphX, making it perfect for the real-time applications. For example, such for maybe fraud detection or real-time monitoring and live analytics. The MLlib is we can say that it Spark's powerful machine learning library that offers scalable and distributed implementations of wide range of machine learning algorithms. So whether it's for classification, regression, clustering, collaborative filtering, or dimensionality reduction, this MLlib provide provides the tool necessary for large-scale machine learning tasks. It also includes modules for feature extraction, pipeline building, and model evaluation, which makes it easier to build and deploy machine learning models. So this MLlib plays a critical role in the domains like predictive analytics, recommendation systems, and data science workflows, which allows you to scale your models across the big data. So when it comes to the graph processing, GraphX is a go-to library. So this module allows you to work with graphs and perform graph parallel computations, making it ideal for the applications like, for example, social network analysis or fraud detection and telecommunications. So GraphX represents the data as nodes and the connections, and it supports the powerful algorithms such as PageRank, connected components, or the shortest path. So by providing the unified API, GraphX simplifies the graph analytics by enabling more efficient and scalable computations. So for the R users, Spark R, it brings the power of Apache Spark to the R programming language. So Spark R allows the R users to leverage Spark's distributed computing capabilities for this big data analytics and statistical modeling. So with Spark R, you can manipulate the data frames, you can run the machine learning tasks through MLlib, you can scale your R workflows to handle the large data sets. So we can say that it is particularly useful for the statisticians or the data scientists who are working in our ecosystem who need to process this big data efficiently. So if we talk about the programming language support, one of the Apache's key strength is its support to the multiple programming languages. So it caters to the developers with the different skill sets and requirements by supporting Python, Scala, Java, R, and the SQL. So Python and Scala are popular for their ease of use and the performance. And while it comes to the R is preferred for the statistical analysis, and SQL support makes it easier to work with structured data. And Java is often used in enterprise environments where integration with the existing systems is crucial. So in short, we can say that Apache Spark ecosystem is designed to be modular yet unified. Whether you are processing batch data or streaming data, or whether you are building machine learning models or performing some complex graph computation, this Spark offers the tools and frameworks to handle it on all together. So from batch processing and streaming to machine learning and graph analytics, this Apache Spark provides a versatile platform that scales efficiently to meet the demands of large-scale data processing. So, in conclusion, Apache Spark has revolutionized the way to handle this big data. With its combination to speed, scalability, and versatility, it empowers the organizations to perform a wide range of data processing tasks across the different domains. So Spark ecosystem is a unified platform that brings together these various components, each specializing in specific aspects of data processing, and which makes it one-step solution for all your big data needs. Now let's see the next concept, which is RDD operations. So in Spark, RDD operations are divided into transformation and actions. So these operations define how data is manipulated and computed in a distributed manner. So the first one is create RDD. So the process starts by creating an RDD, that is nothing but resilient distributed dataset, from an existing dataset or a file. So this RDD serves as a primary abstraction in Spark for the distributed data processing. Here, lineage refers to a metadata Spark that keeps about the transformations which are applied to an RDD. So this keeps a record of all the transformations, and it helps to recover the lost data. If a partition in an RDD is suppose lost, Spark can recompute it using this lineage information. Then transformations are the operations applied to the RDDs that return a new RDD. That means that these are the lazy operation. So what is lazy operation? It means that they do not execute immediately, but instead they define the computational plan that is only executed when an action is triggered. So the example of transformation could be map, filter, flat map, group by, reduce by key, and so on. These transformations are stacked up, and Spark builds a DAG, which is nothing but directed acyclic graph of the operations. but no data is processed until an action is called. So if we talk about the actions, actions trigger the actual execution of the transformations. So they perform the computations on RDD and return the result or store them to an external storage. So examples of action could be count, collect, reduce, first, save, and so on. When an action is called, Spark submits the job for execution, which involves materializing of data, that is, performing all the operations and writing the final output. When an action is triggered, Spark performs the required operation and it produces the result. So this result could be the outcome of transformations or a saved dataset to an external storage. So the key idea is that transformations set up the computation and actions trigger the executions of this computation, and which finally produces the final result. That's it for now. In the next lecture, we will try to cover the points which are getting displayed on the screen. So if you have liked my video, please hit a like to this video and subscribe to my channel. Thank you so much for watching this video, and till then, keep crunching the data.